Hi students, this is Mr. Bob, and in this video, we're going to talk a little bit more about nuclear reactions, and also we're going to start talking about energy sources, which is subtopic 8.1. So as usual, before watching this video, you should have some focus notes set up in your journal or notebook, and have a colored pencil or highlighter ready. And then about 24 to 48 hours after watching this video, there's some Oxford textbook pages that I will be putting in Canvas that you can go and look at to help you fill in, add, group, chunk, or highlight notes, and identify any points of confusion. Okay, so again, recommendations when you're taking notes during this video, please don't write down everything I say, actively listen and selectively write. Pause the video when we have sample problems, make sure you try and work them yourself first. That'll make your brain struggle, help you learn. And if you're still confused, please mark a point of confusion and make a point to ask a question of a classmate or get help from me. 3 essential questions for today. What's meant by the term critical mass when we're talking about a nuclear reactor? What is the difference between primary and secondary energy sources? And what's the difference between specific energy and energy density? Critical mass. So critical mass is what we talk about in nuclear physics when we think about what is required to sustain a chain reaction that we've been talking about, where again, out of a fission, at least one, or on average, one neutron goes on to cause another fission. There's a minimal mass that's required depending on the type of isotope you're using, how well they are enriched, which we're going to talk about in a second, and the geometry. And so this minimum mass of fissionable, which is also known as fissile material, is that minimum mass that's required to sustain the fission process by itself. Okay, so if you have less than that mass, you're not going to have a critical mass. It's going to be subcritical, and you're not going to sustain a chain reaction. If you have more than the critical mass, then you will not only sustain the chain reaction, but you might actually accelerate that chain reaction. One thing that's important to note is that uranium-238 is what we call fertile, meaning it can occasionally fission, but it is not the type of isotope that is fissile, meaning it cannot by itself sustain a chain reaction. It's a different isotope of uranium, uranium-235, which is what we call fissile, okay? And so in order for us to have uranium fuel, like for use in nuclear reactors, what we have to do is we have to take the uranium that comes out of the soil, that comes out of the earth, and we have to enrich it, because over 99% of the uranium that comes out of the soil is uranium-238. A very small portion of it is uranium-235. But we need to enrich that uranium-238 in order to give it enough uranium-235 atoms, isotopes, so we can basically then sustain a chain reaction. One of the ways that we can enrich the naturally occurring uranium that's in the soil is by a process called centrifuging, which I'm going to explain here. So like I said, a reactor needs a higher proportion of uranium-235 isotopes than what occurs naturally. And so one of the means that we've discovered, we've devised, I should say, about how to enrich it is this thing called centrifuging. It's a really neat process, and let me just explain it here. If you look here, I just want to emphasize a couple things about this drawing. Think of this drawing over here on the lower right corner as like a big tube, okay? And you can see this tube has goes in and goes out. So notice what happens here, and this is really important. The uranium that they get out of the soil, what physicists do is they basically mix it, run it through a bunch of chemical processes, and they create what's called uranium hexafluoride. And uranium hexafluoride is actually a gas. So by creating this basically new compound, you're able to make it in gaseous form, and then you're able to feed it into the centrifuge. Okay, and if you've ever used a centrifuge before, you know what happens. You turn it on and it spins. And you can see down here, it shows that this centrifuge, this container is going to spin. Now, the other thing we have to remember, and this goes back to first year physics, if you think about it, more massive items, what are they going to do in a centrifuge? Well, if you think about it, the more massive items, they have more inertia. That means it's harder for them to change direction. So as the centrifuge spins, those more massive items are not going to be able to change direction to keep that spinning motion, as well as lighter items, okay? So the more massive isotopes, i.e. uranium-238, are going to move to the outside, to the outer edges of this spinning container. Whereas the uranium-235 isotopes, which are slightly lighter, are going to stay more in the middle here, okay? So notice what we do. We spin it, And then we provide an outlet for the stuff that's in the middle. And the stuff that's in the middle, like I just said, is going to have a greater content of uranium-235 than the stuff that's on the outside, because it's going to stay more central. And so what happens is this uranium-235 enriched gas is routed out of this centrifuge. And then where does it go? Well, basically it goes right back into one of these containers, okay? Because you have to do this a lot. Just one stage of centrifuging is not going to work. I don't know the exact number, but I know it's in the tens or even hundreds of centrifuges that you need in order to enrich the uranium enough so that you can get something that can serve as fuel in a nuclear reactor. And if you want to make a nuclear weapon, you have to even do this even further, okay? You have to do it to an even greater degree. Okay, so that's centrifuging, and that is one thing that I expect and IB expect you to know, just kind of a general idea of how the uranium can be enriched. Now I want to talk about energy sources, and this, what we're about to talk about here, comes out of the Oxford textbook. So as you saw in the first slide, I'm recommending that you look at the Oxford textbook if you can, sometime during this unit, to help you gain further understanding. First thing I want to talk about is primary versus secondary energy sources. A primary energy source is an energy source which is used to generate electricity or is used directly by a consumer. Okay, that's usually what we think about when we're thinking about energy. So examples of that, if you look here, there's a wood burning stove or a furnace. What does it do? It converts the chemical energy in wood or natural gas to heat your home, okay, or cook your food, and it does that by burning. Other examples of primary energy sources are the things you see there. They're the things we typically talk about: wind energy, coal energy, water, hydroelectric is when we say water, solar energy, natural gas, and nuclear power, which we've been talking about. So what's a secondary energy source? Well, quite simply, a secondary energy source is a source that has been transformed from a primary energy source before it's used by the consumer. And so the two examples that we have are electricity and hydrogen. And of those two, electricity far and away is the most common example of a secondary energy source because it's so conveniently transported and distributed. And it's easy for us to use. Okay, so you should know the difference between primary and secondary energy source and give some examples of each. Now go ahead and grab a calculator if you don't have one yet, because we want to do a little calculation here based on two concepts. There are two important concepts here: specific energy and energy density. For each of the fuel sources I just mentioned, coal, nuclear, et cetera, they have what's called a specific energy and an energy density. When we talk about specific energy, that's quite simply how much energy you can get per unit mass of the fuel. And if you remember back to thermal physics, we had this specific heat capacity, which was the energy required per unit mass to change the temperature of an object. Well, this is the same idea. Remember, whenever you see specific, that usually means mass is involved. So specific energy means how much energy per unit mass from the fuel. So its units are joules per kilogram. Energy density is how much energy you can get per unit volume of the fuel source, and its units are joules per meter cubed. So let's walk through an example here together. We have a fission of uranium-235, and we know that it produces that amount of energy. And we know that the density of the uranium-235 is given there. And so what we want to do is we want to calculate two things. We want to calculate the energy, the specific energy, and we want to calculate the energy density. So let's walk through this together. Okay, and for this problem, we're going to assume all the nucleons in uranium-235 just have the same mass. For our purposes here, the mass difference between a proton and a neutron is not significant. So specific energy, if you remember, is energy per unit mass. Okay, so let's first of all figure out, let's go over to the side here and figure out how much energy is in how much mass is in one uranium-235 isotope, and therefore how much energy it would get if all that mass was converted to energy. So uranium-235, we know it has 235 nucleons. And we know that by what I just gave you, 1.007276 AMU per one nucleon. And we know what's true about the conversion from atomic mass unit to kilograms. This is something that is in your data booklet. 1.661 times 10 to the negative 27th kilograms is 1 AMU. Okay, so let's calculate that. When we do that, we get a number that is 3.9 times 10 to the 25th. So in other words, notice all this that I've done here is going right here in the denominator in mass. So the specific energy is, we know it produces 3.5 times 10 to the negative 11th joules, and that's divided by the number that I just got, which is 3.9 times 10 to the negative 25th kilograms. What does that equal? Oh, let me do this down here. Yes, it'll work best. The specific energy equals roughly 9.0 times 10 to the 13th joules per kilogram. Sorry, my penmanship is not the best today. So that's specific energy. And by the way, you're going to see in a second, that's quite a bit. Okay, now let's calculate energy density. So with energy density, you notice we have, now that we have the specific energy, we can calculate energy density pretty simply. Because notice energy density is 9.0 times 10 to the 13th joules per 1 kilogram. And then notice the problem gives me the density, right? So I want meters cubed on the bottom. I don't want kilograms on the bottom. So notice if I just multiply the specific energy, the specific energy by the density of the uranium-235, notice kilograms cancel, and I'm left with joules per meter cubed. And when you calculate that in your calculator, you should get 1.6 times 10 to the 18th joules per meter cubed. By the way, I should have done this up here as well. Nucleon, nucleon, AMU, AMU, just to make sure we know what we get. Okay. All right, so you should be able to do that. If I give you a problem like that for any sort of primary energy source, you should be able to calculate the specific energy and the energy density. So let's see how the different specific energies and energy densities compare. No. Okay, there we go. This is from Wikipedia, and I think this is really interesting. And so if you look here, what we have is the different types of primary energy sources, okay? Stop, hold on. There we go. These are the primary energy sources for the most part. And you can see there we have a specific energy column and we have an energy density column. And if you just take a moment to look at it, just a couple things I want to point out, which I think are fascinating, is yes, look, all the nuclear stuff is got a specific energy and energy density that is amazingly bigger, so much bigger than anything underneath it. Notice, just look, it's orders of magnitude apart. So this is why you can think and realize that there was a time period where people thought that nuclear power was going to basically solve the world's energy problems, right? There used to be a saying that electricity was going to be so cheap you wouldn't even meter it because you could just sell it for a flat fee, so to speak. That hasn't come to fruition for a lot of reasons. But anyway, you can see why the promise is there, or the possibilities there, given the numbers for specific energy and energy density. Also, I just want to point out all the way down here, at the bottom in terms of specific energy and energy density is batteries. And this is interesting, right? Because we use a ton of batteries in our world. And batteries are really useful to us because they're so portable and we don't have to be connected to the grid. But, and even though battery technology has improved quite a lot in recent years, it still struggles. It still falls behind, far behind in terms of specific energy and energy density. And that has specific repercussions or ramifications as we try and become fossil fuel free. Some of the biggest challenges we have are in the transportation sector, right? Something that no one's really been able to figure out in any concrete way is how to fly planes without fossil fuels, right? There are these electric powered planes are quite limited in their range. And that's largely because, notice here, they become so heavy when you weigh them down with batteries. So heavy, so much so that they can't fly anymore. So that's a big challenge, still presents a big challenge for us. And also heavy trucks. is another big challenge. You don't see electric powered heavy trucks, right? You see electric powered Priuses, passenger vehicles and stuff like that. And that's largely because we still have a pretty significant, these batteries are pretty heavy for the amount of energy they give us. Okay.